In this video, we'll talk about the definition of rigid body. Now, rigid body's definition is that some object that has extended content. Which means that this object is not a point object. It's the first property of rigid body. Now remember the discussion that we made for the previous chapters, we always refer to a point object. And the rationale for that is that we can regard every point of an object, their motion are exactly the same. Then we can say we can simply just think of one point of the object, and that would represent this object's motion. And that was true in the previous chapters. Right? All points of an object, they're having exactly the same motion. Now, one example is the following. Let's say we throw an object in the air. Then this object will just move along this parabolic trajectory. Right? So if you look at this object at any instant, every point on the object, they have exactly the same motion. They have exactly the same horizontal velocity and vertical velocity, etc. And this motion, we're going to talk about this in this chapter. We're going to call it translation. So if an object translates from one place to another place, then every point on the object has exactly the same motion. So that's why we call this object a point object. So that doesn't make a difference. Let's say if I regard this object as a dot, as a point. Okay. Now, second property of rigid body is that because of the extended content of this object, every point will have different motions, and that means that we cannot, so contrary to the point object, we cannot regard every point as the same motion. So let's talk about this rotation. And one way of giving different points different motion is by doing rotation. And we know for a point object, there's no rotation, right? That's just a single point. But for this object, so let me show you. I'm going to just draw same diagram again. So let's say at the beginning, the object still look like this, right? We have these 2 points there. So that we can recognize the orientation of the object. But afterwards, the object may rotate to this new position, its new orientation. So we have these 2 points aligned in that direction. Okay, and later on we can do further rotation. Okay, so it might look the same as this one, but actually this side now goes to here. Okay, so that these 2 points becomes horizontal. So that's how we recognize that for this cube object, right, we do have this orientation for the object. So rotation cannot be neglected. Because now we want to have a much more detailed discussion of this object's motion, including its rotation along a rotation axis. Now, the third property of rigid body is that since the name, right, rigid body, its shape cannot be changed. So it has fixed shape. Now, why this is important? The reason is related to the rotation. So when we describe an object's rotation, we need some physical quantity, right? So we're going to have angles, right, to represent rotation, and angular velocity omega to represent its angular velocity, and also angular acceleration alpha. Okay, now all these quantities can only be defined if the object has a fixed shape, meaning you cannot deform it by compression. So here is one diagram. Let's see. Let me draw a diagram to show you such a concept. So we have a fixed theta omega alpha for any point on the object. Okay, so now let's see the importance of fixed shape. So let's see, here, let's say, is point O, we call rotation axis, going through this point. And we have some initial orientation, let's say, for this point, okay, point 1, with respect to rotation axis O. And there's another point, let's call this point 2, its initial position or orientation with respect to point O. Okay, so now let's see, if this object rotate by some angle, let's say theta angle, okay, then we can say, now I know that angle theta, so I can draw this new position for 1, I call it 1 prime, and the angle between them, right, is theta angle. So the object rotate in a counterclockwise direction. Now the point 2, this point also does the same rotation, okay? But now think about the object can change shape. If it can change shape, then we cannot say exactly the same angle here. Maybe point 2 move to this larger angle. Okay, so you give the name theta 2 and the previous one theta 1. Now, if the shape can change, during the rotation, then we can say theta 1 is not necessarily equal to theta 2. They could be different, right, because of the deformation. Maybe 1 rotate a smaller angle and 2 rotate a bigger angle with respect to the point O. So that means that we cannot have a single variable for describing the object's rotation. And that could happen in real life. We see an object doing rotation. We cannot say for sure that every point have exactly the same rotation. But that's something that we don't want to consider. So that's why in the ideal case, when you talk about an object's motion, we want to say its shape is fixed. Right? During the rotation, we cannot change its shape. So that's why it's important we have this condition here. It guarantees that we have a single set of variables for describing rotation. Okay, so that's the definition of rigid body. So now let's see, are there any properties we need to think for these rigid bodies so that it'll be easier to describe Lizard body's motion. Okay, and actually I already talked about some of them in these two diagrams. So first, there's a translation, right? Translation for this object, for this cube, going from this position to the final position. But in reality, we know the cube can do rotation, right? That's the second picture here. And if you think about the trajectory, this trajectory and that trajectory, it will be the same for one single important point on lizard body, which is called the center of mass. So we can say the translation here, there's a point on the lizard body follow through this parabolic trajectory. Okay, so that's this point here, the same point I use a red dot to represent. And this red dot is the single most important point on this body. You will follow a point particle's motion on the trajectory here. So the translation here is can be described by this dot, by the red dot here, and that red dot is called center of mass. So that's the center of mass doing translation in this process. But we also know it's doing rotation, right? So we cannot forget that. So plus rotation. So that's lizard body's motion. Equals translation plus rotation. But what kind of rotation, right? Rotation can be around any axis. Now it turns out that for this unconstrained lizard body motion, rotation here is around the center of mass. So that's why center of mass is an important concept that we need to discuss first, and then define how to calculate center of mass. And then later on, we can build a coordinate system, like for example, to describe a lizard body's motion. And center of mass would play an important role in such a coordinate system. Okay, so that's why we're going to transition to the discussion of center of mass. Now, what is center of mass? Okay, the definition is the following. Center of mass is, you can think of it as where the location where the gravity acts. So I'm going to use cm here for center of mass. Okay, so center of mass is where the gravity acts. And it is defined as the mass weighted by the position vector of each point throughout the lizard body. Okay, so it may seem abstract. So let's see. Here is some kind of coordinate system. X, Y, and Z. Origin O is here. And we have a lizard body here. And it can be any kind of shape. Now the total mass of lizard body is big M. It's called big M. Now how to define the center of mass? How do we find a single point on this object so that the gravity is acting on it? Okay, so think about a point here, and to make this related to the integral, I'm going to say at this point here, there's a small volume. that's small volume, and there's a small mass dm. Okay, so there's a infinitesimal mass dm inside this object that we picked out, and this dm has a position vector r. Okay, now its contribution to the center mass location is the following. So this r is going to be weighted by dm. So we're going to multiply r by dm. Okay, and we're going to integrate this over the whole body of Lizard body, and then we're going to divide it by the total mass. Okay, and that gives us the center mass position vector. Okay, so R center mass is the center mass position vector, and it's given by the position R, right, weighted by mass dm, integrated throughout the whole body, and then divided by the total mass. You can also think of this total mass as the integral over dm. Okay. Now, in terms of the components, you can say the x component of the center mass equals x component dm integral over m. Okay, and the y component, right, similarly is given by y dm over m, and z component z dm over m. And we'll see some calculation of these kind of integrals later on. But before I do that, let's see, this r times dm, as I said, it's the position r is weighted by the mass dm. Okay, so now think about one simple example. Let's say there's an object that contains two masses. So the Lizard body here include these two balls plus a stick connecting them. Okay, and we can say this side, let's say we're going to call that big M. Okay, the other side called it little m, and big M is greater than little m. Now the stick that connect them, let's think about it as massless. Okay, so it's really tiny mass compared to the other two, and these two masses we can also think of them as like a single dot. Okay, so now if I want to calculate, so here is like a one-dimensional system, and we can build a coordinate system like this. Let's say x-axis. So now the position of the big M is let's call this x big M, and the position of little m, let's call this x little m. Okay, now according to the definition here, R center mass now becomes the x center mass equals position of the big M weighted by the big M, okay, plus position of the little m times little m, and then divided by big M plus little m. So now clearly we can see, because big M is greater than little m, so the contribution of this term is greater than that term. So in terms of the distance between the center of mass and big M and little m, the center of mass position is closer to big M. Or in another word, you can say the center of mass is closer to the heavier side. So the left side is heavier. And right side is lighter. Now I'm going to say the center of mass is closer to the heavier side. So the center of mass is probably here. Okay, so this might seem abstract. So how about let's think about some numbers, and then we'll see the position, okay? The position of the center of mass closer to which side. So now let's say this big M here is 10 kilogram, okay? And little m is 1 kilogram. And then we want to have, let's say, the origin, let's say right here. Origin O is here, okay? And the stick length is, let's say, 1 meter. XM is 1 meter. So let's do this calculation. The center mass equals, continue here, was X big M is 0, right? Times 10 plus 1 times 1 divided by the total mass, 10 plus 1. So get 1 over 11, which is approximately 0.1 meter. Okay, so 0.1 meter compared to 1 meter, right? Of course, it's closer to 0. Okay, so that's why the center mass is closer to the heavier side. Okay, that's a simple numerical example, and also it describes a discrete. So this one is so-called a discrete mass system. But we can already see the importance of the mass distribution. Okay, so the center mass is determined by mass distribution. For a total mass, if you distribute the mass differently, you will get different center mass. Now let's try to do some calculation. Let's say I'm looking at so center of mass example, and the previous example is discrete mass. Now I'm going to do some continuous mass. Continuous mass calculation. Okay, so now let's say there's this triangle. Okay, and we know, let's say the one side is A, that's 90-degree angle, and this side is also A, so we have the two sides of right triangle equal to some parameter A, and we also know its total mass, let's say, is capital M. Now I want to build a coordinate system, let's say along one side of the triangle I have the x-axis. Okay, now the other side, the y-coordinate is going through the vertex here, that's O, and this point, that's y-axis. Okay, so now I want to calculate the center of mass location. Now to do that, let's see, since we're looking at a two-dimensional system, right? So we don't need to draw the z-axis. But we do need to have the integral here. So let's say I'm looking at the center mass along the x-axis, okay? Then that component is given by integral of x dm over total mass m. Okay. Now to do that, we need to think about how to represent the dm here. Okay. So if I pick, let's say, dm for, let me draw a stripe. So if I draw a vertical line here, a second vertical line, okay, and I say that's dm, so that's dm, okay, then all the points on this vertical stripe, right, they have exactly the same x. They all have x here, okay. Now from there we can then calculate the dm, right? We can represent dm that way. So now how to represent this dm? So if you think about the density, and in this particular example is the area density. Let's call it sigma. Sigma equals the total mass over the area of the triangle equals m over the area here. Right? Area of the triangle we know is half a times a. Okay, we know that, so that's why the density is 2m over a squared. Now, in order to figure out the dm, we need to figure out the area of this red stripe. Okay, so red stripe can be regarded as a rectangle, and we're looking at. So let me rewrite something here. Okay, so now the this side we know is a, length is a. Okay, but now I'm looking at the position x to x plus dx. Okay, so the width of this rectangle is dx, and the height, so that's this length. Now the height of this rectangle, right, is this height. But now the question is, what is that height? Okay, now to figure that out, we need to use this the straight line, this straight line's property. So we know this angle is 45 degrees, right? So we can write down a function, let's say y equals x, okay? So this line is along the diagonal, so the slope is tangent 45 degrees, which is 1. And that line will represent the any point along this hypotenuse of the triangle. Okay. Now, if I plug in x, that's this location, and I look up the y coordinate, I will get y equals x. Okay, so that's this height. That's y, which equals x. So that's why the height is actually equals h equals y equals x. Okay, so now we know that then we can calculate the area of the red stripe. The rectangle is given by, so dm area equals the height h times dx, which is x dx. Okay, so now we have everything we need to write out this x center mass. So x center mass equals x dm, right? dm is x dx. Okay, and then the integration here goes from the lower bound for the x goes from 0 here is 0, and the upper bound is a, so it goes from 0 to a. Okay, and then divided by m. Yeah, sorry, I forgot something. So the sigma is the density. Yeah, I forgot the density here. All right, so now that is the integral that we need to do. In fact, sigma is a constant. Sigma is a constant, so we can actually put it outside the integration sign. Okay, so that's sigma over big M, and then we do this integral x squared dx 0 to a sigma over m. Now this x squared integral becomes 1/3 x cubed, and x goes from 0 to a. Okay, now if I plug in the upper bound, I get a cubed, and lower bound give me 0. So we get sigma a cubed over 3m. Okay, now let's put back the sigma's definition right here. I'm going to put it back, so let's see what happens. So sigma is 2m over a squared. Okay, so now I need to multiply a cubed over 3m. Now we can see the 2m's cancel out. This a squared cancel partly with this a cubed, and we have one more a left, and that gives us 2/3 times a. So that's the center mass x coordinate position. Now let's do the same thing for y coordinate. Y center mass equals y dm over m. Okay, now in order to have this y dm again, we need to draw stripes. Okay, but now stripes is not vertical anymore, because along this vertical stripe, all the points will have different y's, and we want to find a stripe that have the same y along the whole stripe, right? So this stripe has to be horizontal. So let me draw a stripe like this. That's the stripe we're looking at. Okay, and let me also extend these two lines so that we know we're going from y to y plus dy. All right, so now let's see, how can we write down this area of the blue area? So remember, when we write down the red area, we use the width dx and height y, which is y or x. Now in this case here, we also have this width we call dy, but now this height. Now height would be horizontal, right? This height, what's this height? We can still use the equation that we found out, y equals x. Okay, so y equals x would represent these, x would represent these length, right? So what we need is the remaining length, and remaining length here is a minus x, right? Since we know this right side of the triangle goes up to a, that's a here, so that's why we have x and a minus x. Okay, all right, so now let's see the area, the blue area, dm area equals a minus x times dy. Okay, but since when we plug it in here to do the dm here to do the integral, we need a y coordinate, right? So that's why I want to change this x to y, a minus y dy, right? Since I know the relation y equals x. Okay, all right, so now we have the elements. We can go back in to calculate y center mass. So y center mass is given by y dm, right? Dm now is a minus y dy, that's the area, and we need to multiply sigma, the density. Now the integral here, the y integral, the y coordinate, right, goes from here, right? That's the initial y, and then up to here. So the y also goes from 0 to a. So this height is a. So we also need to do from 0 to a integral, and then divided by m. Okay, so again, just like before, sigma over m is a constant, so let's pull it out. So now we have integral of the first term is ay, second term is minus y squared, and then dy. Okay, and the integral goes from 0 to a. So now let's see, sigma over m. Now for the first term, we have 1/2 a y squared. For the second term, we get 1/3 y cubed. Now the lower bound is 0, upper bound is a. That's like the integral in a, in x direction. So we have sigma over m. Now for the upper bound, when I plug in a here, I get 1/2 a cubed. Okay, there's another a here, so a cubed minus 1/3 a cubed. Okay, and then we need to subtract the lower bound when we substitute in y equals 0. And it turns out when you plug in y equals 0 here, we get 0, always 0. So that's the final result. And then let me simplify this a little bit. Sigma over m, and then 1/2 minus 1/3 is 1/6 a cubed. Okay, so now let me again plug in sigma's expression from here. 2m over a squared. Now we have a cubed over 6m equals, let's do some cancellations. The m cancel out, a squared cancel with partly a cube, and that's 1, and that's 3. So we get 1/3 times a. So that's the y coordinate of the of this triangle, of the center mass for this triangle. So to summarize, the center mass is at position 2/3 a, 1/3 a. Okay, at least coordinate. Okay, so I hope that show you how to do the calculation of center mass. And in the next video, we're going to talk about another important physical quantity called moment of inertia. And we also do some calculation there to show you how you can determine the moment of inertia of an object. All right, thanks for watching.